Welcome back to the deep dive. Today we're looking at a piece of technology that is effectively the glue holding the entire modern internet together.
That's a good way to put it.
Because if this one component stops working, it really doesn't matter how good your code is or how robust your database is, your
Yeah.
site is just down. We are talking about the load balancer.
It's the traffic cop of the infrastructure world. And the source material today is great because it moves past that, the textbook definition.
Right.
It really gets into the physics of traffic flow. It treats digital requests like, I don't know, water in pipes or cars on a highway.
Which is absolutely the right way to think about it. Because eventually, software hits the hard wall of hardware reality. The source is open with the barista analogy, which I think is just a perfect primer on this stuff.
It's the classic bottleneck problem. You have a coffee shop, that's your server, and one barista.
Oh.
And when a tour bus pulls up, you hit a physical limit. There is a maximum throughput for lattes per minute. Once you exceed that, latency spikes, customers or, packets start timing out, and eventually the barista burns out.
In the shop goes down. And in the old days, the solution was always vertical scaling. You just, hire a faster barista?
Exactly. Or in our case, you buy a bigger mainframe, you max out the RAM, you buy the fastest CPU on the market.
But we all know where that road ends.
Oh yeah. You hit a point where the cost curve just goes vertical. To get like 10% more performance, you have to pay 500% more money.
And even then, you still have a single point of failure.
A very expensive one. If that supercomputer dies, the whole business dies with it.
So the industry pivoted to horizontal scaling. Instead of one supercomputer, let's just run a whole swarm of cheap, disposable commodity servers.
But that creates a new problem. Coordination. If I have 10 servers, how does a user know which one to talk to?
And that is the load balancer's whole job.
That's its entire reason for existence. It sits at the front door, and it creates the illusion of a single system. You hit google.com, you think you're talking to Google, but you're actually talking to a reverse proxy that's routing you to one of 100,000 servers behind the curtain.
So let's dig into the mechanics of that, because the traffic cop analogy suggests it just, waves cars through. But the deep dive highlights that these things make active millisecond decisions based on a request heartbeat.
The heartbeat is the absolute foundation. Before it routes a single packet, the load balancer has to know the state of the backend. It's constantly pinging the servers. These are called active health checks.
It's just asking, are you okay?
Yeah, are you returning at 200 okay? Is your latency under 500 meters? That kind of thing.
And if a server doesn't reply or replies with, say, a 500 error, it's pulled from the rotation immediately.
Right. It's essentially automated damage control.
Yeah.
But the really interesting part is how it decides where to send the healthy traffic, the algorithms.
The sources list the usual suspects, like round robin, which is just one for A, one for B, one for C. It's the default, but it's kind of dumb, isn't it?
It is. It assumes all requests are equal. It assumes every request is a small text file. But if request A is a tiny JSON payload and request B is a 4K video encoding job.
Oh, I see.
Yeah, round robin is going to inadvertently destroy the server that gets the video job if it just keeps piling on more work.
So then you move on to least connections.
Which is reactive. The load balancer looks at the whole pool and says, server C only has 2 active connections right now while the others have 50. Send the new guy to server C. It just smooths out the load naturally.
But the algorithm that stood out to me as, the most practical for modern engineering was the weighted round robin, or weighted least connection.
Oh, this is a huge tool for deployment. It's not just about handling different server sizes, like having one beefy server and 3 small ones. It's about canary deployments.
Right, so this is how you test in production without blowing up the whole site.
Precisely. You deploy your new, maybe buggy code to just one server. You tell the load balancer, okay, give this canary server a weight of 1, give the stable servers a weight of 99.
So only 1% of your users hit the new code.
And if it crashes, you only annoyed 1% of your users. If it holds up, you gradually increase the weight. It's the safest way to ship code.
Okay, there's one more we have to mention just because of caching. IP hash.
Yes. For when you need consistency,
Okay.
right? Sometimes you need a specific user to land on the specific server they were using 5 seconds ago, maybe because that server has their data cached locally.
Sticky sessions.
Exactly. IP hash does a math operation on the user's IP address to ensure they always map to the same backend server.
Although that introduces the concept of state, and as we'll get to, state is the enemy of scaling.
It is indeed.
Let's move to the architectural layers. The deep dives makes a really big distinction between layer 4 and layer 7 load balancing.
Yeah, the guard versus receptionist comparison.
It's a great way to visualize the trade-off. So layer 4, that's your gate guard at the campus entrance.
Yep. He is looking at the vehicle, the TTP packet. He checks the IP address, which is the source, and the port, the destination. He just says, okay, traffic on port 80, go to the web cluster.
But he doesn't open the trunk. He doesn't know what the traffic is.
No context at all. He doesn't know if it's a video, a login attempt, or, a malicious SQL injection. He just forwards packets.
So what's the advantage? Just speed.
Raw speed. He barely touches the data. It's also great for security if you want something called SSL pass-through.
Ah, because the load balancer doesn't actually decrypt the traffic.
Correct. It stays encrypted all the way from the user to the backend server. But modern architectures, especially microservices, they almost always need layer 7, the receptionist.
This is where the load balancer actually opens the envelope.
It terminates the SSL connection,
Sure.
It decrypts the request, and it reads the HTTP headers, the cookies, the URL path, everything.
Which allows for incredibly smart routing.
Totally. You can separate traffic by intent. You can say anything hitting a billing goes to the high security cluster. Anything hitting images goes to the cheap storage buckets.
Or you could even look for a specific cookie, right? Like a premium user cookie.
Exactly. A layer 7 balancer sees that and can route them to a dedicated low latency cluster, while all the free users go to the general pool. You just can't do that at layer 4.
But the cost is that termination. Decrypting and re-encrypting takes CPU cycles. It's heavier.
It is, but in a world of microservices, that intelligence is usually worth the CPU cost.
Okay, so now we get into the chaos engineering side of things, the war stories. Because a load balancer is supposed to prevent failure, but the sources detail some horrific scenarios where it actually accelerates the crash.
The force multiplier effect, yeah.
Let's talk about the zombie server. This is a classic gray failure, isn't it?
It is. A gray failure is so much worse than a total blackout. In this scenario, the server is passing its basic TCP health check. The operating system is up, the network card is blinking.
It looks alive.
It looks alive, but the application logic is dead. Maybe the database connection pool is totally exhausted.
So the load balancer asks, are you there? The server says, I'm here. The load balancer sends a user, and that user gets a 500 error instantly.
And here's the crazy part. Because the server is returning those errors instantly, very, very quickly, the load balancer, if it's configured on least connections, might actually think, wow, this server is processing requests really fast. I should send it more traffic.
It creates a black hole. The load balancer ruthlessly funnels all your users into the one broken server because it looks like the highest performer.
That's it. This is why your health checks need to be deep checks. Don't just ping the port. Make the server run like a dummy database query to prove it can actually do the work.
The other nightmare scenario, and I've seen this happen in real time, is the thundering herd, or the retry storm.
This is the one that keeps site reliability engineers up at night.
So walk us through the mechanics. It usually starts with just a tiny blip, doesn't it?
Usually just one server stalling. Let's say server A gets overloaded for a second and drops a request. The user's client, their browser or mobile app, sees a timeout. So what is it programmed to do?
Retry.
It retries. Now, imagine you have 1 million users, and a small glitch causes 10,000 of them to retry all at once.
You just doubled the load on your system.
Exactly. And the remaining servers start to struggle, so they start timing out.
And then those clients retry again.
And again, it becomes a feedback loop. You aren't just processing traffic anymore, you're processing a tsunami of retries. The load balancer is totally helpless here because the traffic looks legitimate.
So the standard advice is exponential backoff. You tell the client, wait 1 second, then 2, then 4.
Right. But the notes highlight a flaw in that. If everyone backs off by exactly 1 second and then retries at exactly the same time,
You just delayed the thundering herd. You didn't stop it.
you created a synchronized attack on your own servers.
This is where jitter comes in.
Jitter is the savior. You introduce randomness. Wait 1 second, plus or minus a random value. That desynchronizes the swarm. It spreads the retries out over time so the servers can actually recover.
Wow.
I'm serious. If you are building a client that calls an API and you don't have jitter in your retry logic, you are building a DDoS cannon pointed at your own infrastructure.
That is a quote for the office wall right there. Let's look at scaling the scaler. What happens when the load balancer itself gets overwhelmed?
Right, recursive scaling. You have to balance the load balancers. The first layer is usually just DNS. When you look up a domain, you don't get one IP, you get a list. The browser picks one.
But the really cool tech mentioned here is Anycast. It feels like magic.
It really breaks your mental model of how the internet works.
Mm.
We're all taught that one IP address equals one specific machine. Anycast says no, this one IP address exists in London, New York, Tokyo, and Sydney simultaneously.
It's the BGP protocol handling this, right? The routers just say, I'll send this packet to the shortest path.
Exactly. If you're in London, the internet's backbone routes you to the London load balancer. If the London data center goes dark, boom, the BGP routes update, and your next packet goes to New York automatically. It's global infrastructure level failover.
Which is incredible for public traffic. But the source material takes a turn here and introduces the Netflix model. Client-side load balancing.
This is a huge shift in paradigm.
It feels like it removes the traffic cop entirely.
It does. If you are inside a massive ecosystem like Netflix or Uber, you have thousands of microservices all talking to each other. Service A needs to call Service B.
And if you put a hardware load balancer between every single microservice call, you're just adding latency.
Latency and a single point of failure at every single hop. So they move the logic to the client. Service A has a library inside its code like a map that knows the IP addresses of all the Service B nodes.
So it just picks one itself.
It picks one itself. It drives directly to the destination. No middleman.
But, and this is the big warning label in the notes, you can only do this because you own both sides of the connection.
100%.
Yeah.
You have to trust the client. You cannot do this with a web browser. You can't send a list of all your internal server IPs to some user's Chrome browser.
That's a massive security breach.
Yeah. Client-side balancing is strictly for internal service-to-service communication.
Got it. Speed for the internal network, armor for the public one.
We have to wrap up with high availability because we started this by saying the load balancer eliminates the single point of failure, but if you only have one.
You've just moved the single point of failure to a more expensive box.
So who guards the Dardians? The setup is usually active-passive.
It's the standard pattern. You have two load balancers. One is active, sweating, moving traffic. The other one is passive, sitting idle, doing nothing but listening.
Listening for the heartbeat of the primary.
Right. They're connected, often by a literal cable or a dedicated network. The passive one just listens for a pulse, thump, thump. As long as it hears that, it stays asleep.
But if the pulse stops, it initiates a takeover. It broadcasts something called a gratuitous ARP, basically shouting to the entire network, hey, I own this IP address now, and traffic instantly flows to the backup.
But what if the active balancer isn't dead? What if it's just malfunctioning, or the network cable between the two balancers gets cut?
The split-brain scenario, this is so dangerous. If that cable is cut, the passive one thinks the active one died, so it promotes itself. But the active one is still alive.
So they both think they are the boss. They both fight for control of the IP address.
And you get data corruption, drop connections. It's basically a civil war in your server rack.
Which brings us to the solution.
Stoneth.
Shoot the other node in the head.
I know it sounds like a joke, but it is a literal configuration in Linux high availability clusters. If a node suspects the other one is glitching, it doesn't ask it to shut down politely. It uses a remote power management card to physically cut the electricity to the other machine.
It's better to have one dead server than two fighting servers.
In distributed systems, hesitation is failure. You kill the rogue node to save the cluster. It's brutal, but it's necessary.
So looking at all of this, from round robin to Stoneth, what are the big takeaways for the listener?
I'd boil it down to three core principles. First is statelessness. We mentioned it briefly, but it's critical. If you want your load balancer to actually work, your servers have to be disposable.
No saving files to the local disk.
No local files, no local session data. If a user on server A gets switched to server B, they shouldn't lose their shopping cart. That state needs to live somewhere else, like a shared database or a Redis cache. If you're stateful, you're unscalable.
Okay, second.
Observability is not optional. You can't just look at global error rates. As we saw with the zombie server, a global average hides the outliers. You need metrics per node. You need to know if server 42 is returning 100% errors while the rest are fine.
And the third.
Failover needs to be tested. It's not enough to buy two load balancers and plug them in. You need to pull the plug on the primary one during business hours, or at least in a staging environment, and see if Stoneth actually works.
Chaos engineering. If you don't test it, it won't work when you need it.
Hope is not a strategy.
I think that's the perfect place to land. Load balancers are these invisible workhorses, but they embody the most important lesson in engineering. Everything fails. The job isn't to build a system that never breaks. It's to build a system that handles braking gracefully.
And ideally, without the user ever even noticing the carnage happening in the background. But that brings up the split brain problem again. What happens when two load balancers both think they're the boss? That's a chaos scenario for another day.
Thanks for diving in with us. We'll see you on the next one.